Hello and welcome to my presentation on visualization of an electrolysis process using augmented reality. My name is Hilko Aljets and I'm from the University of Göttingen in Germany. Augmented reality is a technology we encounter almost every day. For example, when you take a photo with your smartphone, recognized faces are marked with a box, such as in the image on the right. Azuma and colleagues have defined 3 different characteristics of augmented reality, which are listed here on the left side. The first characteristic is that real and virtual objects are combined in a real environment. In my example, these objects will be the boxes and the camera image. Second, augmented reality runs in real time and interactively. This also applies to my example, as face recognition is executed depending on the camera image. And finally, the real and virtual objects are aligned, so if the faces in my example would move, the boxes would move with them. Augmented reality mixes reality and virtuality, which is illustrated on the next picture, developed by Milgram and colleagues. You can see that augmented reality is more related to the real environment than to the virtual reality. This is because augmented reality is operating in a real and not a virtual environment. The topic augmented reality became more popular in the recent years and a trend in educational research. On the right side, you can see a distribution of publications between the years 2004 and 2020, matching the keywords augmented reality and science education. One reason for this could be the technological development, which made it possible to use the technology on simple mobile devices instead of specialized and expensive equipment. The effects of augmented reality on learning processes are still under investigation, but several case studies show promising educational benefits. In a systematic review, many advantages and disadvantages of augmented reality were identified. One of the most named effects is an enhanced learning achievement as well as an enhanced learning motivation. Future research has to investigate if these effects are caused by a novelty effect. Also, some studies report an increase and some a decrease of students' cognitive load. Literature analysis reveals evidence that augmented reality has the potential to contribute to students' understanding to chemical processes on a molecular level. In order to describe a chemical phenomenon, chemists use 3 different levels of representations which are related to each other: the macroscopic, the submicroscopic, and the symbolic level. Explanations of macroscopic visible chemical processes build on the submicroscopic level to illustrate the movement of particles like electrons, atoms, ions, or molecules, and on the symbolic level to verbalize these processes. For a complete understanding, students need to be able to transfer between these representations. Teaching that considers the interdependency of these 3 levels and focuses on the transfer from one representation to another improves the learning of chemical concepts and reduces the mental load of the students. By showing the movements of the particles to an experiment via augmented reality, the submicroscopic and the macroscopic levels are shown spatial, near, and temporal simultaneously, so that the cognitive load is reduced as suggested by the principles of multimedia design by Meyer. In this presentation, I want to present an application which shows the particle movement on a submicroscopic level during electrolysis of zinc iodide solution. The goal of the app is to provide a model that promotes understanding about electrolysis and facilitates the formulation of the electrochemical half-cell reaction equations. Using the app simultaneously to the corresponding experiments should help students to transfer between the 3 levels of representation and deepens the understanding of the concept of electrolysis. The design is based on some educational considerations, from which I can only present a limited selection. We focused on students' misconceptions about electrochemistry in general and electrolysis, the properties of the virtual objects, and the animation of the reaction. One important design principle was that we wanted to prevent causing new students misconceptions. Therefore, we looked at the most common misconceptions in electrochemistry. The design of the app should ensure that such misconceptions are not evoked. A big challenge was the visualization of the involved particles and objects. It was important for us to show the particles in a correct size ratio. Since the electrodes and wires are much bigger and the electrons are much smaller than the particles, we had to find a compromise between displayability and size ratios. While the particles are shown in a space-filling model, objects like wires and electrodes are displayed in a microscopic way, and the electrons are only represented via text. This results in a mixture of different levels of representation, which was inevitable if the visualization should stay simple. To keep the animation simple, the formation of polyiodides is not shown. The colors and size ratios of the involved particles is based on atomic and ionic radii from literature. We decided to color the spheres of an atom and its corresponding ion similar but not exactly the same, to suggest a relationship between the two. Using the same color could lead to the misconception that the substrate stayed the same. One of the most important features of the app is the possibility to discover the reactions on the electrodes while experimenting. Augmented reality allows the users to walk around the object with the movement of the mobile device and view the process as a whole or in detail. We have implemented information panels about the individual objects, which can be accessed by selecting via touch input and helps to identify them. The animation of the half-cell reactions can be paused and controlled with a trackbar menu to jump forward or backward. This interactivity allows learners to explore the app and study the shown electrolysis at their own pace. After exploring the app, the half-cell reaction equations can be formulated using corresponding worksheets. Here you can see the animation of the oxidation. First, two iodine ions move to the anode and interact with it. The ions oxidize and transfer two electrons to the anode. After that, the formed iodine molecule moves away in solution. On this slide, you can see the reduction reaction. After implementing the basic functions and animations, we asked 10 teacher students for first feedback in an open format. We requested the students to write down anything they noticed on a technical and a content-related perspective. By analyzing their answers, we improved our model and fixed some technical issues. For example, we increased the size of the used font in our information panels. All students recognized the experiment and were able to connect the model with the real experiment. As mentioned earlier, we had to make some compromises in the design of the app. For example, we had to mix the levels of representation by showing the electrodes. Also, we could not display all the involved objects, such as the water of the solution or the polyiodide. We believe it is necessary to critically discuss these limitations with the learners. On the other hand, augmented reality offers a lot of potential for science education. It can positively influence the motivation and learning success of the learners. It is easy to use and could reduce the cognitive load. Nevertheless, future research is needed on the exact impact of augmented reality in education. Thank you for watching this presentation. I would like to thank my co-authors Malte Petersen, Erhard Irmer and Thomas Weiz, and also the student teachers who participated in the mentioned evaluation. If you have any questions or comments, I will be glad to answer them. You can find my email address on this slide.